In January 2025, a quantum computer in California solved a problem that would take the world's fastest supercomputer 10,000 years to complete. It finished in 6.18 seconds. But that's not the strangest part. The strangest part is that according to one interpretation of quantum mechanics, the many-worlds theory proposed by Hugh Everett and championed by physicist David Deutsch, the machine may have solved the problem by accessing alternate versions of itself across parallel universes. What started as a simple light bulb experiment 125 years ago has led us to build machines that operate on principles so bizarre they challenge our understanding of reality itself. To understand how we reached this point, we must travel back to Berlin in 1900, where a simple question about glowing filaments sparked the quantum age, the Silicon Valley quantum revolution. Today, Silicon Valley operates as the epicenter of a technological revolution that most people cannot see. While quantum physics remains abstract to the general public, the reality is far more immediate and dramatic. In 2025, global investments in quantum technology reached over $1.25 billion for quantum computer companies alone, more than doubling the previous year's figures. This massive financial commitment flows into secretive laboratories where engineers build machines that operate on principles so strange they challenge everything we think we know about the nature of reality itself. The world's largest technology companies have entered what can only be described as a quantum arms race. Google's quantum processors now exceed 1,000 qubits and demonstrate computational abilities that seem to violate the laws of physics. IBM has built quantum computers that businesses can rent by the hour, while Microsoft pours billions into quantum software development. These aren't just faster versions of traditional computers. They represent a fundamental shift in how machines process information, and every breakthrough brings us closer to a moment when current encryption methods become worthless overnight. The implications extend far beyond simple computing power. Every password protecting your bank account, every encrypted message on your phone, every secure government communication relies on mathematical problems that take traditional computers to solve. Quantum computers could crack these codes in minutes. The entire foundation of digital security depends on the assumption that certain mathematical operations require enormous amounts of time and computing power. Quantum machines operate under different rules entirely.
These quantum processors exploit superposition, a phenomenon where particles exist in multiple states simultaneously until someone observes them. Unlike traditional computer bits that must be either 1 or 0, quantum bits can be both at the same time. This allows quantum computers to explore multiple solutions to a problem simultaneously, as if they were testing every possible answer in parallel. The effect multiplies exponentially with each additional qubit, creating computational power that grows at rates traditional physics should not permit.
Recent theoretical work suggests an even more extraordinary possibility. Some quantum physicists propose that quantum computers might actually be accessing computational resources from parallel universes. According to the many-worlds interpretation of quantum mechanics, every quantum calculation creates branches of reality where different outcomes occur. When a quantum computer solves a problem, it might be borrowing processing power from alternate versions of itself across these parallel branches. The machine in California that solved the 10,000-year problem in 6 seconds might have been running simultaneous calculations across millions of parallel realities. The year 2025 marked a crucial transition point. Quantum computing moved from laboratory curiosity to practical threat and opportunity. Financial institutions began serious preparations for quantum-resistant encryption methods. Pharmaceutical companies started using quantum simulations to design new medications. Intelligence agencies quietly developed quantum communication networks that promise perfect security through the laws of physics rather than mathematical complexity. The theoretical became operational. The stakes extend beyond any single application. Whoever achieves true quantum supremacy first could break every password, crack every code, and revolutionize everything from artificial intelligence to medical research. Nations have begun treating quantum computing as a matter of national security. China has invested over $15 billion in quantum research infrastructure. The European Union launched its quantum flagship program with similar funding levels. The United States created the National Quantum Initiative to coordinate federal quantum research efforts. Yet quantum computers represent only the beginning of a broader quantum revolution. Quantum internet networks use entangled particles to create communication channels that become more secure when someone tries to intercept them. Quantum sensors can detect gravitational waves, measure magnetic fields with unprecedented precision, and potentially reveal new fundamental particles. Quantum materials promise room, temperature superconductors, and revolutionary energy storage systems. The quantum world operates on rules so bizarre that Einstein himself called them spooky. Particles can be in two places at once. Measurement of one particle instantly affects another particle across any distance. The act of observation changes the outcome of experiments. These aren't abstract philosophical concepts anymore. They're engineering principles that power the machines reshaping our technological civilization. Understanding this quantum revolution requires going back to its origins. The story begins not with abstract mathematics or exotic particles, but with something as mundane as understanding why light bulbs glow different colors when heated. The journey from that simple engineering problem to machines that might access parallel universes represents one of the most remarkable intellectual adventures in human history. The path leads through Max Planck's desperate attempts to solve an industrial heating problem, Einstein's heretical particle theory of light, and decades of experiments that revealed reality itself operates on principles that defy common sense. Each breakthrough built upon the previous one, creating a cascade of discoveries that eventually led to the quantum computers now threatening to transform civilization. The scientists who first explored these quantum phenomena had no idea they were laying the groundwork for a technological revolution. They simply wanted to understand how the universe works at its most fundamental level. Their curiosity about light, matter, and energy opened doors to a realm of physics that seemed impossible yet proved to be the foundation of everything we see around us. The quantum computer that solved the 10,000-year problem in 6 seconds represents just the beginning of this transformation. The same principles that power these machines might soon enable quantum artificial intelligence, quantum-enhanced medical treatments, and quantum materials that could revolutionize energy production and storage. The weird world of quantum mechanics isn't separate from our everyday experience anymore. It's becoming the foundation of the next phase of human technological development. But this extraordinary journey began with engineers facing a problem so simple it seemed almost trivial. They needed to understand why heated metal changes color. That question would crack open the foundations of physics itself and launch humanity into the quantum age. The light bulb mystery that started it all. Berlin in 1900 bustled with the energy of a newly unified nation determined to prove itself on the world stage. The German Empire had emerged just 30 years earlier, and now its leaders possessed an almost desperate hunger to industrialize faster than their European rivals. Steam-powered factories filled the air with smoke while electric streetlights began replacing gas lamps on major boulevards. This was the age of steel and steam, of grand engineering projects and technological optimism. German engineering companies had poured enormous sums into acquiring the European patents for Edison's revolutionary light bulb. These weren't merely business investments, they represented national pride. The light bulb embodied everything the new Germany wanted to become: modern, efficient, and technologically superior. Engineering firms quickly recognized the massive profits waiting in municipal contracts to illuminate the streets of Berlin, Hamburg, and Munich. The German Empire needed thousands of streetlights, and whoever could build them most efficiently would secure a fortune. The German government understood that technological leadership required more than just purchasing foreign patents. In 1887, they established the Physikalische Reichsanstalt in Berlin, a technical research institute designed to give German industry a competitive edge. The PTR represented a new approach to industrial development. Instead of simply copying foreign innovations, German scientists would understand the fundamental principles behind them. This understanding would allow German companies to improve existing technologies and develop entirely new ones. By 1900, the PTR had enlisted Max Planck, an methodical physicist with a reputation for solving difficult mathematical problems. Planck's assignment appeared deceptively straightforward. Figure out why heated light bulb filaments change color as they get hotter. The practical importance was obvious. Understanding this relationship would allow engineers to design more efficient bulbs that produced more light while consuming less electricity. What nobody anticipated was that this simple engineering question would expose a fundamental flaw in humanity's understanding of energy and light. The mystery seemed almost trivial at first glance. Heat a piece of metal with a torch and watch it glow. First it turns dull red, then bright red, then orange, then yellow, and finally white hot. The progression appears logical and predictable. But when Planck examined this phenomenon mathematically, using the established laws of 19th century physics, he discovered something impossible. The equations predicted that heated objects should radiate infinite amounts of energy at high frequencies, particularly in the ultraviolet range. Real objects obviously don't emit infinite energy, which meant the fundamental laws of physics were somehow wrong. This contradiction became so notorious that physicists gave it a dramatic name, the ultraviolet catastrophe. The term captured their complete bewilderment at their inability to explain something as basic as the color of hot metal. Classical physics worked perfectly for calculating the motion of planets, the behavior of pendulums, and the flow of electricity through wires. Yet it failed catastrophically when applied to the simple question of why a light bulb filament glows the color it does. Practical implications frustrated German engineers. They needed to know why blue light was so much harder to produce than red light. Blue light contains more energy per photon, which should make it valuable for illumination applications. But existing theory couldn't explain why heating a filament beyond white hot didn't produce blue light.
The relationship between temperature and light color followed patterns that made no sense according to accepted scientific principles. Planck approached the problem with characteristic mathematical rigor. He collected experimental data on the spectrum of light emitted by heated objects at various temperatures.
The measurements revealed precise relationships between temperature, frequency, and the intensity of light at different colors. But when he tried to derive these relationships from first principles using classical physics, the mathematics led to absurd conclusions.
The equations suggested that any heated object should glow with infinite brightness, radiating unlimited energy across the entire spectrum. The solution came through what Planck initially considered a mathematical trick. Instead of assuming that energy could vary continuously, he proposed that energy came in discrete packets, specific amounts that couldn't be subdivided further. This assumption allowed his equations to match the experimental data perfectly. The energy of each packet was proportional to the frequency of light, connected by a fundamental constant that would later bear his name, Planck's constant. This mathematical breakthrough solved the light bulb mystery completely. The reason blue light was harder to produce than red light was that blue light required larger energy packets. At normal temperatures, there wasn't enough thermal energy available to create these larger packets consistently. Red light, requiring smaller energy packets, could be produced more easily. The progression from red to white hot occurred because increasing temperature provided access to larger energy packets, enabling higher frequency light. Planck himself didn't initially understand the full implications of his solution. He viewed the discrete energy packets as a mathematical convenience rather than a physical reality. The idea that energy might actually come in indivisible chunks seemed to violate everything scientists knew about the continuous nature of physical phenomena. Energy was supposed to flow smoothly, like water from a faucet, not arrive in discrete droplets. The quantum computers that achieved breakthroughs in 2025 rely fundamentally on Planck's insight that energy comes in discrete packets. When quantum processors manipulate individual atoms and photons, they're exploiting the same quantized energy levels that explain light bulb colors.
The superposition states that allow quantum computers to perform multiple calculations simultaneously emerge from the discrete nature of energy that Planck first identified in his light bulb research. The irony remains striking. Planck's investigation of this seemingly simple question about light bulb efficiency accidentally discovered that energy comes in discrete packets, launching the quantum revolution that would eventually transform human civilization. The humble light bulb, symbol of 19th century technological progress, contained within its glowing filament the key to understanding the quantum universe that powers 21st century technology. But Planck's discovery was just the beginning. His mathematical solution to the light bulb mystery would soon inspire another scientist to propose something even more radical about the nature of light itself: Einstein's heretical particle theory. Albert Einstein had been following Planck's quantum energy breakthrough with intense interest, but in 1905 he proposed something so outrageous that it challenged everything scientists thought they knew about light itself. Einstein suggested that light, which everyone knew was a wave, was actually made of particles. The scientific community had spent decades establishing that light behaved as a wave. Experiments by Thomas Young had demonstrated light interference patterns that could only be explained by waves. Scientists could measure light's wavelength and frequency with precision. The wave nature of light seemed as solid as any fact in physics. Then, Einstein proposed that light consisted of individual particles, discrete packets of energy traveling through space like tiny bullets. The suggestion seemed not just wrong, but almost insulting to the accumulated wisdom of physics. Einstein's heretical idea emerged from his investigation of the photoelectric effect, a phenomenon that had been puzzling scientists for years. When light strikes certain metals, it knocks electrons loose from the surface. This seems straightforward enough. Light carries energy, and that energy can dislodge electrons. But the experimental details created an impossible puzzle that violated everything scientists understood about waves and energy. The mystery centered on a completely counterintuitive observation. Weak ultraviolet light could easily knock electrons loose from metal surfaces, while intense red light could not dislodge a single electron, no matter how bright it became. This made no sense according to wave theory. If light was a wave, then brighter light should carry more energy, just like bigger ocean waves carry more power than smaller ones. A massive red light beam should have had more than enough energy to knock electrons free, yet it remained completely ineffective. Consider the analogy of water waves hitting a seawall. Larger waves carry more energy and can knock debris loose from the wall more easily than smaller waves. The height of the wave, its amplitude, determines how much energy it carries.
Similarly, classical physics predicted that brighter light, having higher amplitude, should carry more energy and be more effective at dislodging electrons. Yet experiments showed the opposite. Dim ultraviolet light succeeded where brilliant red light failed completely. The frequency of light mattered more than its intensity, which violated every principle of wave behavior.
Blue and ultraviolet light, with higher frequencies, could always knock electrons loose, regardless of how dim the light appeared. Red light, no matter how intense, never succeeded in freeing a single electron. The cutoff was sharp and absolute below a certain frequency. No amount of light intensity could produce the photoelectric effect.
Einstein's solution was as elegant as it was radical. He proposed that light consisted of individual particles, later called photons, each carrying a specific amount of energy determined by its frequency. Higher frequency light contained more energetic photons, while lower frequency light contained less energetic ones.
A single ultraviolet photon carried enough energy to knock an electron loose, while individual red photons lacked sufficient energy regardless of how many arrived. This particle theory explained the photoelectric effect perfectly. Increasing the intensity of red light simply meant more low-energy photons hitting the metal surface, but since each individual photon lacked enough energy to dislodge an electron, no amount of them could produce the effect. Ultraviolet light, even when dim, consisted of high-energy photons that could each knock an electron free on individual contact.
Einstein himself initially doubted his own theory. The idea that light could be both a wave and a particle simultaneously seemed to violate basic logic. How could the same phenomenon exhibit completely contradictory properties? Waves spread out through space while particles travel in straight lines. Waves can interfere with each other while particles collide. The dual nature seemed impossible to reconcile. The scientific community reacted with similar skepticism. Einstein's particle theory of light appeared to throw away decades of careful experimental work proving light's wave nature. Many physicists have dismissed the idea as a temporary mathematical convenience rather than a description of physical reality.
Even when Einstein won the Nobel Prize in 1921, the award recognized his explanation of the photoelectric effect rather than his famous theory of relativity, highlighting how controversial his quantum ideas remained. Yet Einstein's light quanta theory proved remarkably successful at explaining multiple mysteries simultaneously. The photoelectric effect was just one application. The same particle concept helped explain how light interacts with matter at the atomic level, why certain chemical reactions require specific colors of light, and how solar
panels convert sunlight into electricity. The theory provided a unified framework for understanding light-matter interactions that had previously seemed unrelated. The implications extended far beyond academic physics. Einstein's photons became the foundation for technologies that now power the quantum revolution.
Laser technology relies on the controlled emission of photons with identical energies. Photovoltaic cells convert individual photons into electrical current using the same photoelectric effect Einstein explained. Quantum computers use single photons to carry quantum information between processing units. Modern quantum Internet protocols exploit Einstein's photons to create absolutely secure communication channels. When photons become entangled, measuring one instantly affects the other regardless of distance. This quantum entanglement, which relies on the particle nature of light, enables quantum key distribution systems that can detect any attempt at eavesdropping.
The 2025 quantum communication networks being developed across the globe depend fundamentally on Einstein's century-old insight about light particles. Einstein's heretical particle theory of light solved the photoelectric effect mystery and complemented Planck's earlier work on energy quantization. But the solution created new puzzles that were far more disturbing than the original problems. The idea that light could be both a wave and a particle simultaneously suggested that reality itself might be fundamentally different from human intuition assumed. If light exhibited this impossible
The
dual
electron's
nature,
impossible
what about
dance.
the fundamental building
Scientists
blocks of
at
matter
Bell
itself?
Laboratories in New Jersey were about to discover that matter itself followed the same impossible rules as light. In the 1920s, researchers conducted what seemed like a straightforward experiment with electrons, those tiny particles that orbit atomic nuclei. Everyone knew electrons were solid particles of matter, as fundamental and concrete as marbles or sand grains. Yet when scientists fired electrons at a screen with two narrow slits cut into it, something impossible happened. The electrons created wave interference patterns on the detection screen behind the slits, producing alternating bands of light and dark exactly like ocean waves crashing through two openings in a seawall. This result violated everything physicists understood about particles and matter. Waves create interference patterns because different parts of the wave can arrive at the same location either in phase, reinforcing each other, or out of phase, canceling each other out. When water waves pass through two openings, they spread out and overlap, creating regions where the waves add together and other regions where they cancel out. But electrons were supposed to be particles, not waves. Individual particles should travel through one slit or the other, never both simultaneously. The experimental setup was elegantly simple. Scientists directed a beam of electrons toward a barrier containing two parallel slits. Behind this barrier, they placed a detection screen that would show where individual electrons struck. If electrons behaved like classical particles, they should pass through either the left slit or the right slit, creating two distinct bands on the screen corresponding to the two pathways. Instead, the screen showed multiple bands of varying intensity, the unmistakable signature of wave interference. The implications were staggering. For an interference pattern to appear, each electron somehow had to pass through both slits simultaneously and interfere with itself. This defied all common sense about particles and matter. A baseball thrown at two openings in a fence cannot go through both openings at once. A bullet fired at two doorways cannot pass through both doors simultaneously. Yet electrons, fundamental particles of matter, appear to be doing exactly that. Scientists initially suspected that interactions between multiple electrons might explain the strange results. Perhaps electrons in the beam were somehow influencing each other, creating collective behavior that mimicked wave interference. To test this hypothesis, researchers modified the experiment to fire electrons one at a time, with significant gaps between each electron so no two electrons could possibly interact. The results were even more disturbing. Individual electrons, fired one by one through the double-slit apparatus, still produced the same wave interference pattern. Each single electron somehow contributed to the characteristic banded pattern on the screen, as if each electron was interfering with itself. The first electron might strike the screen at a seemingly random location, but after hundreds of individual electrons passed through the apparatus, the familiar wave pattern emerged. Each electron appeared to be taking both possible paths simultaneously, creating interference between its own multiple trajectories. This phenomenon challenged the fundamental nature of reality itself. Classical physics assumed that objects exist in definite locations and follow specific paths through space. An electron should be either here or there, never both simultaneously. Yet the double-slit experiment suggested that electrons exist in multiple states until the moment of observation. Before striking the detection screen, each electron existed as a wave of probability that passed through both slits at once. The quantum mechanical explanation for this behavior introduced the concept of superposition. According to quantum theory, particles like electrons can exist in multiple states simultaneously until measured. Before observation, an electron does not have a definite position or state. Instead, it exists as a mathematical wave function that represents all possible locations and states the electron might occupy. This wave function passes through both slits simultaneously, creating interference patterns just like physical waves. The act of measurement forces the quantum system to collapse from multiple simultaneous states into a single definite state. When an electron strikes the detection screen, its wave function collapses and the electron appears at a specific location. Before measurement, the electron existed in a superposition of multiple possible locations. After measurement, it occupies just one definite position. This transition from multiple simultaneous states to a single definite state became known as the measurement problem. Modern quantum computers exploit this same superposition principle that the double-slit experiment revealed. Classical computer bits can represent either 0 or 1, but quantum bits can exist in superposition states that represent both 0 and 1 simultaneously. This allows quantum computers to process multiple calculations at once, exploring many possible solutions to a problem concurrently. The same quantum mechanics that allows electrons to pass through both slits simultaneously enables quantum processors to perform parallel calculations that would be impossible for classical computers. The double-slit experiment proved that the quantum weirdness Einstein had identified in light also applied to matter itself. Electrons, atoms, and even complex molecules exhibit wave-particle duality under the right conditions. This discovery established that quantum mechanics governs not just energy and radiation, but the fundamental building blocks of matter. The impossible dance of electrons through two slits simultaneously revealed that reality operates according to rules far stranger than classical physics imagined. These discoveries about the fundamental nature of matter would soon force physicists to confront an even more disturbing question. If particles don't have definite properties until observed, what does that mean for the nature of reality itself? The Copenhagen conspiracy. By the late 1920s, the strange discoveries about electrons and light had created a crisis in physics that split the scientific community into warring camps. At the center of this intellectual battle stood two giants of 20th century science: Niels Bohr, the Danish physicist who had revolutionized atomic theory, and Albert Einstein, whose theories of relativity had already transformed our understanding of space and time. Their conflict would rage for decades, fundamentally changing how humanity thinks about the nature of reality itself. Bohr had developed what became known as the Copenhagen interpretation of quantum mechanics, named after the city where he conducted his groundbreaking research. This interpretation offered a radical solution to the puzzling behavior of quantum particles like electrons passing through two slits simultaneously. According to Bohr's view, quantum particles simply do not possess definite properties until someone observes them. Before measurement, an electron exists in a ghostly state of multiple possibilities. The act of observation forces the particle to choose a single definite state from all the possibilities it previously embodied. This idea struck at the very heart of scientific understanding. For centuries, scientists had assumed that objects possessed definite properties whether anyone observes them or not. A rock has a specific weight, a tree has a definite height, and the moon occupies a particular position in the sky regardless of whether anyone looks at it. Bohr's interpretation suggested that quantum particles operate under completely different rules. They exist in fuzzy, indefinite states until measurement forces them into concrete reality. The implications were staggering. If observation literally creates reality at the quantum level, then the universe operates more like a vast probability cloud than a clockwork mechanism. Before anyone measures a quantum particle's position, it exists everywhere it could possibly be. Before anyone checks a quantum particle's spin, it spins in all possible directions simultaneously. The act of measurement collapses these multiple simultaneous realities into a single definite outcome. Einstein reacted to Bohr's interpretation with deep skepticism and intellectual revulsion. The idea that reality depended on observation violated everything Einstein believed about the universe. He had spent his career discovering elegant mathematical laws that described how the universe operated according to precise, deterministic principles. The notion that fundamental particles existed in indefinite states until observed seemed to reduce physics to a game of chance rather than a science of natural laws. Einstein's objections crystallized in his famous declaration: "God does not play dice with the universe." This statement captured his conviction that the universe should operate under deterministic laws, where every event has a definite cause and effect. Random probability might describe human ignorance about underlying processes, but it could not represent the fundamental nature of reality itself. Einstein believed that quantum mechanics was incomplete and that a deeper, more complete theory would restore classical determinism to physics. The debate between Bohr and Einstein played out in conferences, scientific papers, and personal correspondence throughout the 1920s and 1930s. Einstein repeatedly proposed thought experiments designed to expose contradictions in quantum mechanics. He searched for scenarios where quantum predictions would lead to absurd conclusions, hoping to prove that the theory was fundamentally flawed. Bohr responded to each challenge with careful, analysis that defended the Copenhagen interpretation while acknowledging its strange implications. Despite Einstein's persistent objections, the Copenhagen interpretation gradually gained acceptance among physicists. The interpretation worked extraordinarily well for predicting experimental results and developing practical applications of quantum mechanics. Scientists could calculate the probability of various outcomes with remarkable precision, even if they could not explain why individual measurements produce specific results. The theory's practical success outweighed its philosophical difficulties. The Copenhagen interpretation became the foundation for all modern quantum technologies. Quantum computers rely on the principle that quantum bits can exist in superposition states, representing multiple values simultaneously, until measurement collapses them into definite states. The quantum processors developed in 2025 exploit exactly the same indefinite quantum states that Bohr described in his interpretation. These machines maintain particles in superposition while performing calculations, then measure the results to extract useful information. Quantum cryptography systems use the Copenhagen interpretation's measurement principle to create perfectly secure communication channels. Any attempt to intercept quantum encrypted messages necessarily involves measurement, which disturbs the quantum states and reveals the presence of eavesdropping. The security of these systems depends fundamentally on the idea that observation changes quantum reality, precisely what the Copenhagen interpretation predicted. The Copenhagen interpretation, despite its bizarre implications, had become the foundation for quantum mechanics and modern quantum computing. The debate between Bohr and Einstein appeared settled through experimental verification and technological application. Reality seemed fundamentally uncertain at the quantum level, and that uncertainty had become the key to humanity's most advanced technologies. Yet Einstein refused to surrender. His most powerful challenge to quantum mechanics centered on a phenomenon he discovered that seemed to violate the very laws of physics he had established. This phenomenon would become his final attempt to prove that quantum mechanics was incomplete, though it would ultimately provide the foundation for technologies he never imagined possible. Einstein's spooky action challenge. Einstein's most ambitious challenge to quantum mechanics emerged from his collaboration with Boris Podolsky and Nathan Rosen in 1935. Their thought experiment, known as the EPR paradox, focused on a quantum phenomenon called entanglement that seemed to violate the most fundamental principles of physics. Einstein believed this phenomenon would finally expose the incompleteness of quantum theory and restore common sense to the universe. Quantum entanglement occurs when two particles become connected in such a way that measuring one instantly affects the other, regardless of the distance separating them. Einstein found this idea deeply disturbing because it appeared to allow instantaneous communication across any distance, directly contradicting his theory of relativity. According to relativity, nothing can travel faster than light, yet entangled particles seem to influence each other instantaneously across the entire universe. The EPR thought experiment worked like this. Imagine two particles that become entangled and then fly apart to opposite ends of the galaxy. According to quantum mechanics, neither particle has definite properties until measured. But the moment someone measures one particle and finds it spinning clockwise, the other particle instantly becomes locked into spinning counterclockwise, even though it might be billions of miles away. This instantaneous correlation seemed to require faster-than-light communication between the particles. Einstein called this phenomenon spooky action at a distance, and argued that it proved quantum mechanics was incomplete. He refused to believe that measuring one particle could instantly affect another particle across vast distances. Such instantaneous influence would violate the principle of locality, which states that objects are only directly influenced by their immediate surroundings. A particle here on Earth should not be able to instantly affect a particle on the other side of the galaxy. To make the strangeness more concrete, consider an analogy with spinning coins. Imagine you have two magical coins that are entangled with each other. You flip one coin in New York and it lands heads up. At that exact moment, the other coin in Tokyo automatically becomes tails, even though nobody touched it. This instantaneous correlation happens faster than light could travel between the two cities, seemingly violating the speed limit of the universe. Einstein proposed a more reasonable explanation: hidden variables, instead of particles existing in indefinite states. Until measured, he suggested that particles always possessed definite properties determined by variables that quantum mechanics could not detect. These hidden variables would be established when the particles first became entangled, like programming both coins to show opposite results before sending them to different cities. When someone measured one particle, they would simply reveal a property that already existed, eliminating the need for instantaneous communication. The hidden variable theory restored common sense to physics. Particles would have definite properties whether anyone observed them or not, just like ordinary objects in everyday experience. The correlations between entangled particles would result from their shared history, rather than mysterious instantaneous connections. Einstein believed that discovering these hidden variables would restore determinism to physics and eliminate the probabilistic weirdness of quantum mechanics. For decades, the debate between Einstein's hidden variables and quantum mechanics remained unresolved. Scientists could measure the correlations between entangled particles and confirm that quantum mechanics predicted these correlations accurately, but they could not definitively prove whether hidden variables existed. The questions seemed to be more philosophical than scientific, involving interpretations of reality that might be impossible to test experimentally. Modern quantum communication systems exploit entanglement to create perfectly secure communication channels. The quantum communication market reached $1.2 billion in 2025 and is projected to grow to between $10.5 billion and $14.9 billion by 2035, representing a compound annual growth rate of 22 to 25%. These systems use entangled particles to distribute encryption keys that become more secure when someone tries to intercept them. Any attempt to eavesdrop on quantum encrypted messages necessarily disturbs the entangled particles, revealing the presence of unauthorized access. Quantum internet networks use entanglement to create instantaneous correlations between distant locations, enabling applications that would be impossible under classical physics. Scientists have demonstrated quantum teleportation, which uses entanglement to transfer quantum states between particles over arbitrary distances. This technology promises to connect quantum computers across the globe, creating a quantum internet that could revolutionize computing and communication. The quantum cryptography systems protecting sensitive communications in 2025 rely fundamentally on the spooky action at a distance that Einstein hoped would disprove quantum mechanics. Post-quantum cryptography algorithms are being developed to withstand attacks from quantum computers that exploit the same entanglement phenomena Einstein found so disturbing. The security of these systems depends on the instantaneous correlations between entangled particles that seem to violate the principles of relativity. Einstein's objection to quantum entanglement inadvertently identified the quantum phenomenon that now enables unhackable quantum communication networks. The faster-than-light correlations he found impossible to accept became the foundation for technologies that promise to revolutionize cybersecurity and digital privacy. Yet the fundamental question remained unanswered. Was Einstein right about hidden variables? Or did quantum mechanics truly describe a universe where particles could influence each other instantaneously across any distance? The resolution would require a test so ingenious that it would settle the debate about the nature of reality itself. Bell's brilliant test of reality. John Bell worked at CERN, the European Particle Physics Laboratory, but his most important contribution came from a simple question that had haunted him since graduate school. Could you actually design an experiment to determine whether Einstein or quantum mechanics was correct about the nature of reality? Bell's answer would transform abstract philosophical debates into concrete experimental tests that could settle the matter once and for all. Bell's breakthrough came through mathematical analysis of the correlations between entangled particles. He realized that if Einstein's hidden variables existed, They would place strict limits on how strongly two entangled particles could be correlated when measured. These limits became known as Bell's inequality, a mathematical boundary that local realistic theories could never exceed. However, quantum mechanics predicted that entangled particles could violate this inequality, producing correlations stronger than any hidden variable theory could explain. The mathematical framework was elegant in its simplicity. Bell's inequality states that certain combinations of correlation measurements must remain below a specific threshold if local realism governs the universe. Local realism combines two assumptions: locality, meaning that objects are only influenced by their immediate surroundings, and realism, meaning that objects possess definite properties whether observed or not. If these assumptions were correct, the correlations between entangled particles will be bounded by Bell's inequality. Testing the fundamental nature of reality required transforming Bell's abstract mathematics into concrete experimental procedures. Bell's insight was to focus on statistical correlations between measurements performed on entangled particles under different conditions. These correlations would reveal whether the universe operates under local realism or quantum mechanical principles. The experimental design resembled an elaborate card game where the dealer represents quantum mechanics and the players represent different measurement choices. Imagine a dealer who claims to possess two special cards that always show opposite colors when revealed simultaneously. The dealer shuffles the cards and sends one to Alice in New York and another to Bob in Tokyo. Alice and Bob can choose to examine their cards using different colored filters, essentially asking different questions about their cards' properties. If the cards operate under local realism, their properties are determined when the dealer first shuffles them. Alice's choice of filter cannot affect Bob's results because her card cannot communicate with his card faster than light. The correlations between their measurements would be limited by the constraints of local realism. But if quantum mechanics governs the cards, Alice's choice of measurement can instantly affect the correlations with Bob's results, potentially violating Bell's inequality. Bell's work initially met with complete indifference from the physics community. His 1964 paper introducing Bell's theorem was largely ignored, receiving minimal citations and generating little discussion. Most physicists seemed uninterested in testing the fundamental nature of reality, preferring to focus on practical applications of quantum mechanics. The lack of immediate recognition reflected the physics community's general reluctance to engage with foundational questions about quantum mechanics. The situation changed dramatically in the 1970s when experimental physicists began developing techniques sophisticated enough to test Bell's inequality. Alain Aspect at the University of Paris-Sud led the most famous series of experiments, using entangled photons to measure correlations under different conditions. These experiments required extraordinary precision to ensure that measurement choices were made independently and that no communication could occur between the entangled particles. Aspect's experiments used pairs of photons created by exciting calcium atoms with lasers. When these atoms decayed, they emitted two photons that remained entangled despite flying apart at the speed of light. The experimenters measured the polarization of these photons using different filter orientations, essentially asking different questions about the photon's properties. The correlations between these measurements would reveal whether local realism or quantum mechanics correctly described reality. The results were unambiguous and shocking. The correlations between entangled photons violated Bell's inequality, exceeding the limits that local realism could permit. Quantum mechanics was correct, and Einstein's belief in local realism was wrong. The universe operates under principles that allow instantaneous correlations between distant particles, defying common sense about space, time, and causality. These experimental results proved that quantum entanglement was real and that the universe is fundamentally non-local. Particles can be connected across arbitrary distances in ways that classical physics cannot explain. The act of measuring one particle instantly affects its entangled partner, regardless of the space separating them. This discovery validated quantum mechanics while overturning centuries of assumptions about the nature of reality. Modern quantum technologies exploit these non-local correlations that Bell's tests verified. Quantum cryptography systems use entangled particles to create communication channels that become more secure when someone attempts to intercept them. The quantum internet networks being developed worldwide rely on entanglement to create instantaneous connections between distant quantum computers. Bell's test proved that quantum entanglement is real, opening the door to technologies that might access parallel universes. The violation of Bell's inequality demonstrated that reality operates under principles far stranger than classical physics imagined. The same non-local correlations that shocked Einstein now power quantum computers that exploit the fundamental weirdness of quantum mechanics to perform calculations that should be impossible. The theoretical foundation was now complete. Scientists had proven that quantum mechanics accurately described reality, no matter how strange its implications seemed. The stage was set for engineers to build machines that could harness these bizarre quantum phenomena
The quantum
for
computing
practical
breakthrough.
applications that would
October
transform
2019
2019 marked a pivotal moment in computing history when Google announced that their Sycamore quantum processor had achieved something unprecedented. The machine solved a computational problem in approximately 200 seconds that would have taken the world's fastest supercomputers an estimated 10,000 years to complete. This demonstration, dubbed quantum supremacy, represented more than just a faster computer. It proved that quantum machines could harness the fundamental weirdness of quantum mechanics to perform calculations that classical physics considered impossible. The achievement sent shockwaves through the technology industry, but 2025 brought even more dramatic breakthroughs. Google's quantum chip, Willow, with 105 qubits, demonstrated significant advancements in error correction and performance, allowing it to perform complex calculations exponentially faster than supercomputers. This progress in error correction proved essential for achieving the stability and accuracy needed to deploy quantum applications at scale, marking a turning point in the industry. The development of Willow and its error correction capabilities signaled a shift from the development phase to the deployment phase, indicating that quantum technology was nearing commercial relevance. Microsoft joined the quantum revolution in February 2025 with their first quantum chip, the Majorana 1, which harnesses the properties of a material called a topological qubit. This new chip was expected to accelerate drug discovery, battery development, and the race toward artificial intelligence dominance. The development of the Majorana 1, with its potential for more efficient and less complex error correction, could help avoid quantum decoherence, which happens when a quantum system loses its quantum properties and starts behaving more like a classical computing system. Understanding how quantum computers achieve these impossible feats requires examining the quantum mechanical principles that power them. Unlike classical computers that process information using bits that must be either 0 or 1, quantum computers use quantum bits that can exist in superposition states representing both 0 and 1 simultaneously. This fundamental difference allows quantum machines to explore multiple solutions to a problem concurrently, processing vastly more information than classical computers can handle. Quantum computers also exploit entanglement, the spooky action at a distance that Einstein found so disturbing. When quantum bits become entangled, measuring one instantly affects the others regardless of distance. This creates correlations between different parts of the quantum processor that classical computers cannot achieve. The combination of superposition and entanglement enables quantum computers to perform calculations that would require classical machines to run for longer than the age of the universe. The implications for cryptography and digital security are staggering. Modern encryption systems rely on the mathematical difficulty of factoring large numbers into their prime components. Classical computers would need centuries to factor the numbers used in current encryption schemes, making them practically unbreakable. However, quantum computers running Shor's algorithm could factor these same numbers exponentially faster, potentially breaking every password, cracking every encrypted message, and rendering current cybersecurity methods obsolete. The US government and other entities closely track quantum computing's development, due to its implications for encryption. The Biden White House stated in 2022 that a cryptographically relevant quantum computer could jeopardize civilian and military communications, undermine supervisory and control systems for critical infrastructure, and defeat security protocols for most internet-based financial transactions. This recognition has led to focused efforts on developing post-quantum methods to secure data against future quantum attacks. The current state of quantum computing represents a remarkable acceleration in capability. IBM has developed quantum processors with over 1,000 qubits, while Google's error-corrected systems demonstrate unprecedented stability and accuracy. These machines are no longer laboratory curiosities, but practical tools that businesses and researchers can access for real-world applications. The quantum advantage has moved beyond theoretical demonstrations to practical problems in drug discovery, financial modeling, and artificial intelligence. Pharmaceutical companies are using quantum computers to simulate molecular interactions with precision that classical computers cannot achieve. These simulations accelerate drug discovery by allowing researchers to test millions of potential compounds virtually before moving to expensive laboratory experiments. Financial institutions employ quantum algorithms to optimize trading strategies and risk assessments, processing market data in ways that reveal patterns invisible to classical analysis. Some interpretations of quantum mechanics suggest an even more extraordinary possibility. The many-worlds interpretation proposes that quantum computers might actually be borrowing computational power from parallel universes. According to this view, every quantum calculation creates branches of reality where different outcomes occur. When a quantum computer solves a problem, it might be accessing computational resources from alternate versions of itself across these parallel branches. This interpretation explains the exponential speedup that quantum computers achieve. Instead of processing information sequentially like classical machines, quantum computers might be running parallel calculations across multiple universes simultaneously. The quantum computer that solved the 10,000-year problem in 200 seconds might have been distributing the calculation across millions of parallel realities, each contributing a small piece to the final solution. The 2025 developments in quantum error correction represent crucial steps toward practical quantum advantage. Error correction addresses the fundamental challenge of maintaining quantum states long enough to perform useful calculations. Quantum systems are extremely fragile, losing their quantum properties when disturbed by environmental noise. Advanced error correction techniques allow quantum computers to maintain coherence for extended periods, enabling complex calculations that require many sequential operations. The quantum computers operating in 2025 achieved practical quantum advantage in multiple real-world applications, not just theoretical problems. These machines are beginning to transform industries, accelerate scientific discovery, and challenge our fundamental understanding of computation and reality itself. Yet the computational breakthroughs represent only one dimension of the quantum revolution. The same quantum phenomena that power these extraordinary machines are also enabling an entirely different kind of transformation in how information travels across the globe. The quantum internet revolution. Quantum communication networks represent the next frontier in this technological revolution. Scientists and engineers are constructing a quantum internet that promises to transform digital security forever. This network operates on principles that make eavesdropping not just difficult, but physically impossible, using the same quantum entanglement that Einstein called spooky action at a distance. The foundation of this quantum internet rests on quantum key distribution, a method that exploits quantum mechanics to create perfectly secure communication channels. Unlike traditional encryption that relies on mathematical complexity, quantum key distribution provides security through the fundamental laws of physics. When two parties share quantum-encoded information, any attempt to intercept that information necessarily disturbs the quantum states, immediately alerting both parties to the breach. This built-in intrusion detection makes quantum communication ideal for sectors where data security is paramount, such as defense, finance, and healthcare. The race to build global quantum internet infrastructure has become a matter of national security and economic competitiveness. The European Union advances quantum communication through the European Quantum Communication Infrastructure Initiative, which aims to integrate quantum-based technology into existing communication networks. This project collaborates with the European Space Agency to develop a quantum-secure space communication network using quantum key distribution to detect any interception attempts. The goal is to enhance the security of sensitive data and critical infrastructures across Europe by creating a continent-spanning quantum communication network. China has achieved remarkable progress in quantum communication through its Mischius satellite, launched in 2016 as part of the Quantum Experiments at Space Scale project. This satellite has successfully demonstrated quantum key distribution over more than 1,200 kilometers, establishing ultra-secure communication links between ground stations. In a landmark achievement, Mischius enabled intercontinental quantum key distribution between China and Austria, proving that quantum communication can operate across global distances. These demonstrations show that quantum internet infrastructure can span continents using satellite networks to connect terrestrial quantum communication systems. The quantum internet operates differently from traditional networks, focusing on security and integrity rather than speed or bandwidth. This specialized network serves as a complement to the classical internet, providing ultra-secure communication for applications that demand maximum protection. The quantum internet is designed to coexist with existing infrastructure, creating a two-tiered system where sensitive communications travel through quantum channels while routine traffic continues using classical networks. Quantum teleportation represents one of the most extraordinary capabilities of quantum communication networks. Despite its name, quantum teleportation does not transport matter, but rather transfers quantum states between particles across arbitrary distances. This process uses entanglement to create perfect copies of quantum information at distant locations while destroying the original, ensuring that sensitive data cannot be duplicated. Researchers at Northwestern University successfully teleported the quantum state of a photon across 18 miles of fiber optic cable used to carry internet traffic, marking the first time researchers were able to transport quantum internet traffic over infrastructure designed for traditional internet traffic. The development of quantum repeaters represents crucial technological advances for long-distance quantum communication. Quantum repeaters amplify quantum signals without destroying their quantum properties, enabling quantum communication across continental distances. These devices address the fundamental challenge of quantum communication. Quantum states are extremely fragile and lose their properties when disturbed by environmental noise. Startups and major technology companies are racing to develop quantum repeaters and other hardware components, even while the software market remains relatively small. The implications for privacy and security extend far beyond current encryption methods. Quantum communication networks could protect sensitive government communications, secure financial transactions, and enable private medical data sharing with unprecedented security guarantees. The quantum internet promises to make digital communication absolutely secure while enabling new forms of distributed quantum computing that could revolutionize scientific research and technological development. Current quantum internet projects in China, Europe, and the United States demonstrate different approaches to building quantum communication infrastructure. China emphasizes satellite-based quantum communication networks that can span continents without requiring extensive terrestrial infrastructure. European projects focus on integrating quantum communication into existing fiber optic networks, creating hybrid systems that combine classical and quantum channels. American research emphasizes developing quantum repeaters and memory systems that can extend quantum communication distances using terrestrial infrastructure. The transformation of cybersecurity and digital privacy through quantum communication represents a fundamental shift in how we protect information. Traditional encryption relies on mathematical problems that are difficult for classical computers to solve, but quantum computers could potentially break these encryption methods. Quantum communication provides security that remains intact even against quantum computer attacks, creating a new paradigm for protecting sensitive information in the quantum computing era. The quantum internet's impact on global communications could be as revolutionary as the original internet's effect on human society. Secure quantum communication networks could enable new forms of international cooperation, scientific collaboration, and economic interaction. Organizations could share sensitive data without fear of interception. Researchers could collaborate on quantum experiments across continents, and governments could communicate with absolute security guarantees. The quantum internet revolution transforms the fundamental nature of secure communication by harnessing quantum mechanics to create communication channels that become more secure when someone attempts to intercept them. This represents a complete reversal of traditional cybersecurity, where security weakens under attack. Yet the quantum phenomena powering these revolutionary technologies may not be confined to carefully controlled laboratory environments and engineered quantum systems. Quantum biology and consciousness. Scientists began discovering quantum effects operating in the most unexpected places, inside living cells. For decades, researchers assumed that quantum mechanics could only survive in the sterile environments of physics laboratories, where temperatures approach absolute zero and particles remain carefully shielded from disturbance. The quantum world seemed fundamentally separate from the warm, wet, chaotic environment of biological systems. Then experiments revealed something extraordinary. Quantum effects don't just survive in living organisms. They actually power some of the most essential processes of life itself. The discovery began with photosynthesis, the process that allows plants to capture sunlight and convert it into energy with nearly perfect efficiency. Scientists had long puzzled over how plants achieve this remarkable feat. When sunlight hits a leaf, it creates tiny packets of energy called excitons that must travel through a complex maze of chlorophyll molecules to reach the reaction center, where energy conversion occurs. Classical physics predicted that these excitons would wander randomly through the chlorophyll network, losing most of their energy as heat before reaching their destination. Recent experiments revealed something impossible according to classical expectations. The excitons don't follow random paths through the chlorophyll molecules. Instead, they behave like quantum waves, exploring all possible routes simultaneously until they find a most efficient pathway. This quantum coherence allows plants to achieve energy transfer efficiency that approaches 100%, far exceeding what random molecular motion could accomplish. The warm, noisy environment of plant cells should destroy quantum coherence within picoseconds, yet somehow these biological systems maintain quantum effects long enough to power photosynthesis. The European robin provides another striking example of quantum biology in action. These birds navigate across thousands of miles during migration using a magnetic compass located in their eyes. The mechanism depends on a chemical reaction triggered by incoming light. When a photon enters the robin's eye, it creates an entangled pair of electrons within specialized proteins called cryptochromes. The Earth's magnetic field influences the quantum state of these entangled electrons, affecting the outcome of subsequent chemical reactions that generate the bird's directional sense. This quantum compass demonstrates how biological systems can maintain entanglement, the spooky action at a distance that Einstein found so disturbing. The robin's eye operates at body temperature in a biochemically active environment filled with molecular vibrations and electromagnetic noise. Yet the quantum entanglement between electrons survives long enough to provide navigational information. The bird essentially uses quantum mechanics to detect magnetic fields with extraordinary sensitivity, enabling transcontinental migration with remarkable precision. Human perception itself might rely on quantum effects. Scientists are beginning to realize that our sense of smell may involve the vibrations of molecules rather than just their shapes. The traditional lock and key model of smell suggested that odor molecules must fit precisely into receptor sites, like keys fitting into locks. But this model cannot explain why molecules with completely different shapes sometimes smell identical, or why molecules with similar shapes can smell entirely different. The quantum theory of smell proposes that scent molecules are playing music for our noses. According to this theory, receptor molecules contain quantum particles that detect the vibrational frequencies of odor molecules through quantum tunneling. Different molecules vibrate at different frequencies, and our quantum receptors can distinguish between these molecular vibrations. This mechanism would make our sense of smell much more like our sense of hearing, detecting the quantum music of molecular vibrations rather than just molecular shapes. Quantum tunneling also plays crucial roles in biological processes, such as the metamorphosis of tadpoles into frogs. Enzymes break down the tadpole's tail by severing strong protein bonds that classical chemistry says should be impossible to break at body temperature. Quantum tunneling allows protons to pass through energy barriers that would normally block chemical reactions, enabling the rapid breakdown of the tadpole's tail and subsequent rebuilding of the frog's new limbs. Without quantum tunneling, this metamorphosis would be impossible. These discoveries raise profound questions about the nature of consciousness itself. Some researchers propose that consciousness might emerge from quantum effects in the brain, particularly in structures called microtubules found within neurons. These protein structures could maintain quantum coherence long enough to influence neural processing, potentially explaining aspects of consciousness that classical neuroscience cannot address. The idea remains controversial, but it suggests that human awareness might depend on the same quantum phenomena that power photosynthesis and bird navigation. Research in 2025 continues to explore quantum effects in the brain and their applications in quantum biology. Scientists are developing quantum technologies that could enhance medical imaging techniques, optimize treatment personalization, and improve diagnostic accuracy. Quantum technologies are projected to contribute up to $503 million to the global healthcare industry by 2028, with a compound annual growth rate of 42.5%. The survival of quantum coherence in biological systems challenges fundamental assumptions about the relationship between quantum mechanics and the macroscopic world. Living cells operate at temperatures and in environments that should destroy quantum effects almost instantaneously. Yet evolution has apparently found ways to harness quantum phenomena for essential biological functions. This suggests that the boundary between the quantum and classical worlds is far more permeable than scientists previously believed. The possibility that life itself is fundamentally quantum mechanical represents a revolutionary shift in our understanding of biology. The quantum world that seems so strange and separate from everyday experience might actually be the foundation of life itself, powering the processes that enable plants to capture sunlight, birds to navigate across continents, and humans to perceive the world around them. Yet these discoveries about quantum biology raise an even more fundamental question about the nature of quantum mechanics itself, the multiverse and what it reveals about the structure of reality. David Deutsch, a physicist at Oxford University, proposed a radical explanation for quantum computing's extraordinary power that connects directly to these biological quantum phenomena. According to Deutsch's interpretation, quantum computers might be accessing computational resources from parallel versions of themselves across the multiverse. This theory emerged from Hugh Everett III's Many Worlds interpretation of quantum mechanics, first proposed in 1957 as a graduate student at Princeton. The Many Worlds interpretation eliminates the mysterious wave function collapse that troubled physicists for decades. Instead of quantum particles choosing single outcomes when measured, Everett suggested that every possible outcome actually occurs in separate branches of reality. When you measure an electron spin, the universe splits into multiple realities, one where you observe spin up and another where you observe spin down. Both versions of you exist, but in separate parallel universes that can never directly communicate. This interpretation addresses quantum mechanics most persistent puzzle without requiring particles to magically choose definite states from multiple possibilities. The double-slit experiment becomes straightforward under this view. Each electron actually does pass through both slits, but in different branches of reality. In one universe, the electron passes through the left slit. In another universe, it passes through the right slit. The interference pattern emerges from interactions between these parallel realities, each contributing to the final result we observe. Quantum entanglement becomes equally logical under the many-worlds framework. When two particles become entangled, they remain connected across all branches of the multiverse. Measuring one particle doesn't instantly affect its distant partner. Instead, you discover which branch of reality you inhabit based on your measurement results. The correlations between entangled particles exist because the same quantum events that determined one particle's state also determined its partner's state across all branches of the multiverse. The implications extend far beyond abstract physics. Every quantum measurement splits reality into multiple branches, each representing a different outcome. Every decision, every interaction, and every quantum event creates new universes. The number of parallel realities multiplies exponentially with each quantum event, creating an infinite multiverse where every possible version of history unfolds simultaneously. There are versions of you who made different career choices, versions who never encountered quantum mechanics, and versions living in worlds where these discoveries never occurred. Recent theoretical work explores whether we might detect evidence of these parallel universes. While direct interaction seems impossible, some physicists suggest that subtle effects might provide indirect evidence of other realities. Gravitational anomalies, unusual particle interactions, or statistical patterns in quantum measurements might reveal the influence of neighboring universes. The detection of such effects would require extremely sensitive experiments and advanced theoretical models, but the possibility remains scientifically viable. The connection between quantum computers and parallel universes represents one of the most extraordinary implications of the many-worlds interpretation. When a quantum computer performs calculations using superposition, it might be distributing the computational work across multiple universes, with each universe contributing to the final result. This perspective offers a radical explanation for quantum computing's exponential speedup over classical machines. Consider how this might work in practice. A quantum computer with 300 qubits can exist in superposition states, representing 2 to the power of 300 different configurations simultaneously. According to the many-worlds interpretation, each of these configurations might correspond to a different universe where a parallel version of the quantum computer explores one specific solution path. The quantum computer you observe represents just one branch of reality, but it benefits from computational work performed by its parallel versions across the multiverse. This interpretation suggests that the quantum computer that solved the 10,000-year problem in 200 seconds might have been distributing the calculation across an astronomical number of parallel universes. Each universe contributed a small piece of the solution, and the quantum computer you observe simply represents the branch that received the combined results. The machine didn't just calculate faster than classical computers. It borrowed computational power from parallel versions of itself across the multiverse. The mathematical framework supporting this interpretation remains rigorous despite its seemingly fantastical implications. The Schrödinger equation, which governs quantum mechanical systems, naturally describes the evolution of multiple parallel realities without requiring additional assumptions. The many-worlds interpretation simply takes the mathematics of quantum mechanics seriously, following the equations wherever they lead without imposing arbitrary restrictions. Recent theoretical work on quantum gravity explores how space-time itself might be subject to quantum fluctuations. These theories suggest that the structure of reality could branch at the most fundamental level, creating new universes through quantum processes that affect the fabric of space and time. This research aims to unify quantum mechanics and general relativity, potentially providing a comprehensive description of how the multiverse operates. Experiments in 2025 continue testing the foundations of quantum mechanics, with implications for understanding the multiverse. These experiments probe the limits of quantum theory and explore whether observed quantum phenomena require the existence of multiple universes. While we cannot directly observe parallel realities, the statistical patterns in quantum measurements might reveal indirect evidence for or against the many worlds interpretation. The ultimate question remains: are we living in a quantum multiverse where every possibility becomes reality across infinite parallel worlds? The many-worlds interpretation suggests that reality is far stranger and more expansive than we ever imagined. The quantum computers achieving breakthroughs in 2025 might be accessing resources from across infinite realities to solve problems that would be impossible for any single universe to tackle alone. What began as abstract theoretical speculation has become the foundation for technologies that are reshaping human civilization. The technologies emerging from these quantum discoveries now stand poised to transform every aspect of human society. The journey from Max Planck's light bulb mystery to quantum computers that might access parallel universes represents humanity's most extraordinary intellectual adventure. What began as a simple engineering problem in 1900 Berlin has become the foundation of technologies that could reshape civilization itself. The quantum technology market is projected to reach $106 billion by 2040, driven by advances in computing, sensing, and communication that exploit the very weirdness Einstein called spooky. The universe's deepest mysteries have become the keys to our greatest technological achievements, transforming the impossible into the inevitable through quantum mechanics.